All right. Hello, everyone. Welcome to another episode of the Vive Center seminar, talking about issues about augmented reality and virtual reality. And today we're going to have a speaker, Vivek Nair. And so before his talk, let me give you guys a little background of Vivek. He is an NSF Cyber Corps scholar, the NTSC Fellow, the Hearst Foundation Fellow, IC3 researcher, and currently is a PhD student at the EECS at the UC Berkeley. And he is passionate about cybersecurity and dedicated to defending digital infrastructure through applied cryptography. And he was previously the youngest ever recipient of the bachelor's degree and master's degree in CS from the University of Illinois before he joined Berkeley. And outside his research, he is a co-captain of the Cal VR esports team, and he led the team to achieve a U.S. National Collegiate Championship in 2021. And I think he's going to give a talk about unique identification in virtual reality, and he's going to present his findings, and then hopefully we have about 5 to 10 minutes for discussion after that. Yeah. All right, so the floor is yours.
Great, thank you for the great introduction. I normally leave the VR part out, but I felt it was appropriate for this talk. As Dr. Yang mentioned, I'm going to be talking today about an identification study using over 55,000 virtual reality users. Before I get into it, I want to also mention that I was one of many authors on this paper. So we had an amazing team behind this project. I want to thank my advisors, Professor O'Brien, Dr. Louis Rosenberg of Unanimous AI, and Professor Don Sons, as well as our excellent postdoc Wenbo, our two graduate students, Justice from University of Westphalia and Rui from Berkeley. And also quickly acknowledge our funding is from the National Science Foundation, National Physical Science Consortium, Hertz Foundation, and the Berkeley Center for Responsible Decentralized Intelligence. And with that out of the way, I'm going to take you back about 50 years, which is where this research gets its origin, to this study from 1977 from Cutting et al. And this is a study on one of the original studies on human motion data. So people have known for quite a while that everyone has slightly different motion patterns, whether it be gait, the way you walk around, the way people gesture when they talk, right? People's motion is all unique, and that's due to a combination of things like physiology, but also muscle memory, learned behaviors. We've known this for a while, but this was one of the first studies in 1977 that actually demonstrated empirically that humans can identify each other just based on motion. So not looking at the person, the silhouette or anything, but just looking at movement, we have this natural, kind of weird natural ability to identify each other. And what they did is they had these 6 people walking around in a lab, right? So just that they had this lab setting. And this is before sophisticated computer graphics or anything like that. So they just attached these lights, these markers to the person's body, to various points in the body. And then they just took a video feed, plugged it into a television set, and literally just cranked up the contrast ratio until all you can see is these markers, these lights moving around. You can't see the person anymore. And so this is what it actually looked like from the lab study. And then they just showed these videos of the people moving around to some buddies of the participants, right? So there's these people who are all friends with each other, and they said, hey, just based on these lights moving around, can you name who you're looking at right now? And it turns out that they could do this with a decent degree of accuracy, not great accuracy, about 40%, but that's highly still statistically significant result. Better than random, people can just look at these lights moving around and name who they're looking at.
How many people would they have?
6 people. And
6 people.
Yeah,
okay.
What do you want to study?
Okay.
Yeah. So, this is the first, right? So this is just proving the point all that time ago. And it's weird because this is not something that we really practice, right? No one really practices identifying their friends based on motion. This has to be something that we just naturally pick up for some reason. Now, the reason this should be interesting to us here today as virtual reality researchers if we think about, the type of data that's being collected in virtual reality, so at a minimum, you have a headset and you have two controllers, and you're capturing those three tracked objects, 6 degrees of freedom in three-dimensional space. You're just tracking these 3 points moving around, right? And then in virtual reality, and especially in a metaverse setting, not only are you streaming this data, these three tracked objects, to an application so that it can render frames and stimuli for the user, but if you're in a multi-user metaverse environment, you're also going to be streaming that to some server, and even to other users, random users around the world potentially are seeing this data of these points on your body moving around, right? And that type of data should seem very familiar to us because it's exactly the same type of data that we have known for almost 50 years is enough to uniquely identify individuals. So this observation right here, that VR tracking data looks very similar to point light markers, which are known to be identifiable. This observation is essentially the basis of the privacy research in VR, right? And we're certainly not the first ones to make this observation, that this data looks very familiar. So in fact, there have been a number of studies before us that have investigated the identifiability of VR motion data. And these are generally lab studies where various universities have gotten between 30 to as many as 500 users into a lab, had them use a VR device and told them to do some task, right? That some of them were, an archery or a bowling game, but some of them were just sitting and watching a video in virtual reality. And then they record all that telemetry data, that tracking data of those users, and put it into some machine learning model to see whether they can identify those users, whether they can tell apart all of the users just based on the sensor values captured by this VR device. You can see here the accuracy rate achieved by these prior studies. Some of them are pretty high as 95%, right, with this Miller et al. Study with 500 users. So that tells us that there is something here, right? The prior work has already shown that, okay, if you have 500 users, and just to point out the obvious, right, that the difficulty of identifying a user is linearly proportional with how many users you have, right? If you have 2 users, you can flip a coin and be correct half the time. So when you have 500 users and you're looking at their motion and saying which of them they are 95% of the time, there is something there that is unique about motion. This is how we know that this is a legitimate field of research to be interested in. But although this result seems quite impressive, there is something hidden behind the surface, which is that using these 3 points on the body, you can actually just get some static measurements of your user, right? For example, with the headset on your head, if you take the distance between that and the ground, then you're just measuring the person's height, right? And similarly, if someone puts their hands out to the side and they're holding 2 controllers, then you can measure their wingspan. And so there's a variety of just static measurements of the person that you can take from this data. And it turns out that, and we'll show a statistical analysis later that kind of indicates this, that just these static measurements of height and wingspan and so on could be enough to identify up to 4,000 users uniquely. So when you look at these previous studies with 30 to 500 users, they don't necessarily prove that the unique motions are being used to identify people, right? They prove that there's some data there, but it could just be static identifiers. So for context, and just to spoil the result a little bit, the study we're going to present today is all the way over here, right on the graph. So 55,000 users while still achieving 94% identification accuracy, almost on par with the prior work. And the way we do this, right, so obviously we did not get 55,000 people into a lab and have them use VR. So we actually do this from using a game called Beat Saber, which happens to be one of the most popular VR games and VR applications, period, of all time. It's actually a driving force behind VR adoption in general. And so this is a game with over 6 million players. And for those of you who aren't familiar, it's basically a rhythm game. So there's you're standing in VR, you're holding a lightsaber type thing in each hand. And there's a song playing in the background, right? And then in time with the beat of this song, there are these objects flying at you, which could be either blocks that you have to cut with the correct hand in the correct direction, or it could be bombs that you have to avoid. Essentially, you have to perform tasks. If you mess up too many times, you'll fail the level and have to start again. But if you do a good enough job, you'll get a certain number of points. You'll get a score of how well you did on that level. And there's a lot of these levels that people have built. And so because you can keep trying it and doing better and better over time, there's developed quite a big competitive scene around this game where people are constantly playing this game, trying to get better and better scores. And because of that, there's actually developed these leaderboard, people have developed these leaderboard websites where you can go and upload your score and you try to be the highest score on the leaderboard. And the interesting thing about these leaderboards, which makes it a great opportunity for research, is that when you upload your score, when you set a high score at a map, you're not just reporting your number, oh, I got 1 million points, right? Because then people could just fabricate their performance. So whenever you upload your performance to this leaderboard, you're actually also capturing a recording of your entire gameplay in that session. And then that recording of the motion data is automatically attached to your replay. So now we have these centralized replay services, which are repositories of a huge amount of motion data from VR, more than we could ever hope to get from a lab study. And if we look at this data, I called it a recording, but it's actually just these three tracked objects, right? Headset and two controllers, and they're tracked in 6 degrees of freedom. So if you think about what this data actually is that we're looking at, you have 18 measurements at any given time, right? 6 degrees of freedom times 3 objects. And those 18 measurements are taken between 60 and 144 times per second. So that's fundamentally what we're talking about here when we talk about the replays or the recordings. It's not really an audio and video recording. It's more like just capturing the position and orientation of these objects over time. And when we look at how many users, so there's, as I said, millions of Beat Saber players, but the number of players who have actually submitted replays to this service, that's about 55,000 users, slightly over that. And those users, so not only do we have a very large sample size, right, compared to any other study of this type, those users are also demonstrating a good degree of ecological validity. So these are users from over 40 different countries, using over 20 different types of VR devices. So everything from the oldest, Oculus CV1 to the newest brand new headsets, inside out tracking, outside in tracking, right? You have a huge diversity of the sample here because this is not people coming into a lab and participating in a study. This is data of natural VR users who are just playing a game, on their own time, basically. And so if you look at the actual number of those recordings or replays that we have, it's about 2.7 million recordings that we analyzed. So 2.7 million, captures of motion data of people playing this game. And even if we split it into sessions, which I'll talk about in a second here, you're still looking at about 700,000 sessions of VR usage.
For those users, when you get the data that describe their motion, do they know beforehand that so they are in participate in the research, or they are not aware of that?
That's a good question. So what they know is that they are uploading their motion data, right? Because these are not just users who are naturally playing Beat Saber. These are users who have to go out of their way to install this mod called Beat Leader. Okay. And the whole point of that mod is to upload motion data to the internet for people to see. Okay. Then these replays become publicly available on the internet for anyone to see. And so the data that we're using for this study is all sort of already publicly available. Okay. Right. So, and it ends up being about 4 terabytes of data, a huge amount of data just to capture all of these VR users. So this is a data set. This is how we're actually able to achieve such a huge and representative sample size in the study. If we look at an individual user, right, the pattern of replays, the pattern of scores being submitted to this leaderboard looks something like this here. So it's not, evenly distributed. You have users who are setting scores in clusters, and this makes sense because if you're going to play Beat Saber, you're often not going to play just one song. you might play for 30 minutes, and you might set 5 scores at a time. And the reason this is relevant is that we actually want to cluster these into distinct usage sessions in order to split them appropriately for an identification study. If you think about it, right, within a single usage session, there are a lot of attributes that are captured by this motion data that are not really about the user, but are just specific to the session. So a simplest example is just where you're standing in the room, right, and which way you're looking. So if we're capturing these coordinates in 3D space, and that's just where you are in your room, right, then within a session, it's going to be really easy to identify you, because we're going to say no one else was standing exactly that place in their room, looking exactly that direction. But we don't really want to do that, because that's not really identifying the user. It's more like identifying the specific session. This is also, potential drawback of the previous research, including the Miller study with 500 users, right? Because they had people come into a lab just once, they're actually looking only within one session at identifying users. And so where people happen to be standing in that lab, right, that actually could have an effect on identification. So here we want to avoid that effect of picking up on session-specific metrics. And so we make sure for all of our 55,000 users to split up the data in such a way that some sessions are put into a training set, some sessions are put into a testing set, and we have a couple of other sets here that I'll talk about. But this guarantees essentially that when we're identifying a user, the motion that we're using to identify them is not only from, it's not only motion data that the model hasn't seen, but it's from an entirely different day usually than the data the model has trained on. So it represents a more realistic attack scenario for that reason.
So you never put the training, the data from the training date into testing?
So sometimes people have multiple sessions within one day, but we never put the same session.
Okay.
Yeah. I mean, most of the time the sessions are from different days. And so, right, so basically the goal with this is that you take some combination of these 3 sets, training, validation, and clustering, and you use this data to train some machine learning model that is designed to ingest the motion from those sessions and try to learn how each user moves a little bit differently. And this is supervised learning, so we're telling the model which user it's looking at during training, but then when we test, we take this data again from a completely different day, completely different session. And just based on that motion data, so it's now learned all 55,000 users, we ask it which user it's looking at. And ideally, so if this model is well suited for the problem, then it should be able to output the ID. Oh, this motion looks like it was coming from this exact user. So that's the goal. Now I'll tell you a little bit about how we actually accomplish this, right? Because in order to do this, we need to take this motion data, which is sequential. It's this sequence, this series of frames that are being captured. And we need to feed that in the model in a way that it understands the time series nature of the data. And there are actually machine learning models that can do this natively. So we think about sequential or recurrent neural networks, things like LSTM models, right? Newer transformer-based models can do this as well. The problem, though, is that if you're trying to build a multi-class classifier with 55,000 users, then you're going to have this output layer that has 55,000 neurons, right? And then you think about the sequences and the input layer, and these are up to 140 frames per second. Some of these replays are, 6, 7, 8 minutes long. So we're also looking at tens of thousands of neurons on the input layer. Suddenly you have this massive model that's really hard to train and converge. So deep learning, in our evaluation, we found that deep learning didn't perform as well for the models that we tested. And what we found is that actually this model called LightGBM, which is a tree-based model, ends up providing the best performance for this type of problem. And this is also consistent with what a lot of the prior identification studies found as well, which is that some kind of random forest-based model tends to provide the best performance. And LightGBM just goes a step further than the forest of decision trees architecture used by the prior studies. It adds a layer of gradient boosting on top of that. So the model is essentially not only training an ensemble of decision trees to classify which user it's looking at, but also has this layer of deciding which tree is going to be the best at classifying an individual user. So that's the idea with this light GBM approach. And the problem, right, is that because it's a tree-based model, it's expecting some kind of tabular data set. It's expecting rows and columns. It's not really designed to ingest sequential information. And so the way we convert this continuous motion into features that a tree-based model can understand is essentially with just a statistical summarization approach. Again, pretty consistent with the prior work. And so what we do is we look at the three objects that we're tracking, head, left hand, and right hand. And for each of those objects, you have 3 position coordinates, right? And then you have 4 rotation coordinates, because we use a quaternion representation of orientation. And so you end up having 7 dimensions that you're tracking times 3 tracked objects. So for each of those dimensions, we just take a statistical summary over 1 second of motion. So looking at 1 second of movement, we take the minimum, maximum, mean, median, and standard deviation, right? And so if you look at those statistics across all of your dimensions, you end up with this 105-dimensional statistical summary of 1 second of motion, right? And this then takes your continuous motion data into a tabular format with 105 columns and sort of 1 row for every second in your replay. It turns out this does a pretty good job of extracting the key information to describe the motion. But we wanted to go a step beyond this, because it's one thing to capture motion data in a vacuum. It's another thing to really understand what the user was doing at that point in time, and then allow the model to understand the motion not only on its own, but in the context of what was happening in the virtual world, right? Because if you can learn how users actually react to the same events in the virtual world, then you have a much better ability to tell apart users based on different reactions to the same event, right? Doing kind of a more apples to apples comparison.
Vivek, I want to ask another question here.
Yeah.
So in here, you said 105 dimensions. I guess you start with you have 3 sensors, right? So basically, your data are collected from the head and the left hand and right hand. And from each of them, you calculate within 1 minute. Is it 1 minute or 1 second?
1 second.
1 second of mean, max, mean, median, and the standard deviation.
Yeah.
That is 1 second. Yeah. But then you cross with the position and rotation. What the position and rotation has to be instantaneous, right?
Yeah. So we're looking at within 1 second, those values, position and rotation, are going to be captured around between 60 and 144 times in 1 second. Okay. Right? So you have for each,
and then you do stack them together.
You take the stats of each of those vectors across 1 second of motion. So for example, for 1 second.
Oh, you don't put the instantaneous reading into the classifier. You only put the mean and max and the mean.
Exactly.
Okay, so you just put the statistics of that.
The statistics of that.
So you don't concatenate them. Okay.
It's not concatenated. Okay. Yeah. Yeah, and the statistics are more meaningful than instantaneous data. So it turns out that if you look at an individual frame, it's highly noisy measurement, right? Mm-hmm. But these summary statistics give you a much better measurement of a trend across a second of motion. But like I was saying, it's even more meaningful in context, right? So if you think about a virtual event, right, at any given time, a user is going to be reacting to some kind of stimulus that's provided by the VR device. And we found that there's this set of measurements, which are 22 measurements. I'm not going to go through them individually, but there's 22 measurements that accurately characterize a virtual event that a user can be reacting to, particularly in this application context. And those are things like, what are the position and location of the virtual object? What is the user's motion and speed relative to that object, right? Things like that. So if we think about a Beat Saber block, for example, like I said, there's 22 what we call context features, contextual features that summarize the event itself. And then if you look at those 105 motion features that I mentioned earlier, and you take the 1 second period leading up to that event, and you give the 105 motion features for that 1 second. And then you also take the 1 second period directly after that event, and you give, again, the summary statistics for that, and you concatenate those together, right? Now you have a 232-dimensional feature vector that really accurately characterizes a virtual event and the user's reaction to that event. So you have a challenge response or stimulus response pair that is encoded into one set of features. And this provides really powerful identification characteristics because it's allowing the model to see, it's allowing the model to directly observe learned behaviors in the form of reactions to events. So that's our featureization approach. This is our approach for converting those recordings into a tabular data set that the model can understand. And all we have to do at this point is we have these sets that I mentioned earlier, right? So taking the replays, let's say a user has 100 sessions that they've played Beat Saber. What we would do is we would put 70 of those sessions into the training bucket. We would put 10 of those sessions into validation bucket. We'd put 10 into clustering, and we'll put 10 into testing. I'll explain what those are in a minute. But of course, making sure that there's at least one session in each of those sets at a minimum. And then from that entire set of sessions in each bucket, we just derive a small number of features randomly from that set. For training, we derive 150 features. And so each of those features or each of those samples has those 232 dimensions, right? And then for the other three sets, we derive 50 features each. So that means that no matter how much the user has played Beat Saber, no matter how much data we have, we're using at most 5 minutes of data to train on each user, and at most about 100 seconds of data to test on each user in the end. And then what we do is we just put these features through a z-score normalization, and it's essentially centering each of these 232 axes around its own statistical mean, and scaling it to its own variance, right? And that's all. So that gives you the final feature vectors. So now we're almost there. So now we have taken our Beat Saber recordings and we've converted it into a feature format that is really conducive to identification. The only remaining problem, right, is that given the best performing model is LightGBM, if we were to try to take all 55,000 users and build one gigantic multi-class classifier with LightGBM, this would still be really hard to train and converge because LightGBM has this quadratic training time with respect to number of classes. And it's actually sort of within the realm of feasibility. So this would take around 7 days, would require around 4 terabytes of memory. That's not out of the realm of possibility for a data center distributed training approach, certainly. But, of course, eventually you might have 100,000 users, right? And also as researchers, we want to be able to rapidly iterate. We don't have to wait 1 week to try every hyperparameter combination, right? So this is, we wanted to find a more scalable way to do this than wait 1 week for every run of this model. And the way we ended up doing this is using a hierarchical model. So essentially the way this works, instead of training one massive 55,000 class classifier, we train 10 or so smaller classifiers, each of which are looking at a subset of the users, 10% of the users. And then we repeat that whole process again, right? Train another 10 classifiers, but now each of them are looking at a different subset of the users. So in this first round, every user is in exactly one classifier. In the second round, every user is in exactly one classifier, but they're going to be in different classifiers. And then when you're trying to find out which user you're looking at, when you're doing a testing run, you're just going to feed that data into all 20 of your classifiers that you have now. And it turns out that what happens is that even the classifiers that haven't seen this user at all, which is most of them, they're still going to come up with some output. They're going to say, which of my users is it most similar to? But both of the layers have seen different users. And the models that haven't seen the real user from a given motion set are going to come up with generally different answers for which user they think it is. On the other hand, the models, the two models that actually have seen the target user are very likely to agree on the output. So what this means is by training a large number of small classifiers, you can kind of put them together in this hierarchical order to create a, essentially one big composite classifier with almost the same degree of accuracy. So this is a technique we used for scalability. And then we actually did one more thing on top of that, which is using this clustering set that I mentioned earlier. So this is essentially, it's called deconfusion layer, and it's essentially like a trial run. Doing a trial run, what if we were to evaluate the approach right now? How well would it do? Right? And so you take this motion data from the clustering set, and you say, okay, for each of these users, if I were to put it into this model right now, would they be correctly classified or not? And for most of the users, this is enough. So for about almost 90% of the users, this will already do a good job of identifying them. But for some users, this current model is going to get it wrong, right? Maybe the two similar users happen to be in the same model in both layers, and so they weren't able to be fairly compared. So for those users, what we do is we actually build a graph, so an undirected graph, one node per user. And every time this current model confuses two users, it gives the wrong output, we just add an edge between those two nodes in the graph, right? And then just by taking the connected components of this graph, you get all of the sets of users who are likely to be quite similar, all the users who are likely to be confused with each other. And what we do is we then just build a third layer where we make sure that all of the users who are the most similar are directly compared with each other in at least one model. So we have this third layer of classifiers. And then just for testing, we'll use all three of these layers now to give the composite output for each user. That's our overall approach. And here's how it did in practice. So if we look at the accuracy of each layer, so this is where the 94% result comes from. Oh yeah, hopefully there we go. So 94%. If you put all three layers together, that means that you take anonymized motion from one of your users, you ask the three layers which user I'm looking at, and out of the entire 55,000 users, just based on the motion, they're going to pick the correct user 94% of the time. So this is a pretty significant result, and it's actually dependent as well on how many seconds of data you test on. So we have up to 100 seconds. It turns out if you take just one sample of that 232 dimensions that I mentioned earlier, so that's 2 seconds of data, and you just use that 2 seconds in this model and you say which user is this, and it still identifies the correct user almost 50% of the time. So for almost half of the users, 2 seconds is enough time to identify which of the 55,000 they are. And then it, of course, increases the more seconds, the more samples you have. So if you look at 10 seconds of data, so if you enter VR, you move around for 10 seconds, I'll know who you are almost 75% of the time. And then it keeps increasing. You have 83% for 20 seconds, all the way up to 100 seconds. This is where our 94% result comes from.
Question. So in here, when you say 2 seconds, 10 seconds, 20 seconds, do you still maintain the same number of features, or it was partly because 2 seconds, the number of features is less? Because if you give the full 5 minutes, you do get, if I remember, like 100 something features. But when you are concentrated in 2 seconds, do you get less features?
Exactly, you get less features. Yeah, you get one feature actually, only one feature. So this is just providing one row of this table and saying which user is it. But it's pretty remarkable that you can still almost half the time get the right user just by watching someone for 2 seconds. They half of all people reveal their identity within 2 seconds, right? So now the obvious question that you might have at this point is basically, how is this working, right? What is it about motion that allows all of these people to be identified uniquely just based on how they move around? And we've done actually a couple of statistical analyses to try to answer this question of how this is working, and also what this means for various users in the real world. So one of the analyses that we did is a key impact factors analysis. And what we did is we have a lot of metadata for these users as well. We didn't use this metadata at all to train or test the models, but we're just using it now to understand the performance. And this metadata includes things like what device someone is using, what country are they from, how much experience do they have playing the game, right? And it turns out that all of these different attributes that a user may have impact how easy it is to identify them in general. And there's some interesting trends here. So you might have noticed one of them is that certain devices are a lot, the users of certain devices are a lot easier to identify than others. So something like a Windows mixed reality device, right, has notoriously poor tracking characteristics because it's using a lot of dead reckoning as opposed to a high quality tracking source. And this means that the data is low quality, which is actually bad for usability, but it's good for the user in terms of anonymity. You just can't get precise enough measurements to identify them quite as accurately. right? On the flip side, something like a Valve index, you can identify those users significantly better because of the high quality outside-in tracking. Another thing that's kind of interesting here is that the country is a big impact on how identifiable someone is, right? And this goes, this is more stronger effect than you might even imagine. So if a user is from Korea or Japan, they can be identified with almost 99% accuracy. And this is not identifying those users within that country. This is if you are from Korea or Japan, you can be identified globally with 99% accuracy just by virtue of being from those countries. So that's pretty interesting, really strong trend. But of course, here the biggest trend that shows up in our analysis is the number of replays, right? This is by far the biggest impact on identifiability. And this may seem obvious to some extent that, hey, the more replays that you have, the more data that we have, of course we can identify you better. We have more data, right? So this is a graph that shows for users basically how many times have they played the game, right, on the x-axis versus how accurately we can identify them on the y-axis. The thing is that it's actually not as simple as that. It's not as simple as we have more data about you, so therefore we have more information to identify you. Because as I said, for every user, no matter how many times they've played, we always take exactly 5 minutes of data for training and up to 100 seconds of data for testing. And even users who have played 1 or 2 times have already, 5 minutes of data or more. So it's not as simple as, we have more data. What this actually shows is that the more you play a game in virtual reality or use an application in virtual reality, the more you develop and reinforce application-specific muscle memory, right? And this is pretty interesting. So for the users, Beat Saber users who have played 100 times or more, so some of the more dedicated users, we can actually identify them with 99.5% accuracy. So these are, at a certain point, you become very, very identifiable. The reason being, at least in part, because the first time you're playing a game, you're basically flailing around, you're trying to figure out the rules, you don't know how stuff works. By the 20th time or so, you have a good picture of how, the rules are pretty simple. It only takes a few minutes to learn. And then you're just kind of at that point reinforcing your muscle memory. So you've committed to a certain play style and you're developing your own unique style and reinforcing that over time. So this is one of the key indicators that motion is actually really important for how users are being identified in this particular study. Because no matter if you are playing for the first time ever or your 100th time, the static features are going to be there. Your height, your wingspan, that doesn't change whether you're a new or expert user. So the thing that changes whether you're a new or expert user is the way you move. And that is what is having a huge impact on accuracy. We can actually show this in a more direct way using a model explainability analysis. So this is one of the great benefits of using a tree-based model. Unlike a deep learning model, we can actually do pretty easily, feature importance explanation. And what this graph is showing is the percentage of overall entropy. So if you think about information gained about a user as a certain number of bits of Shannon entropy. So for each of the features, you're seeing here all 232 features from an event. And for each of the features, how much entropy is being gained from that feature, right? And so what I've done is I've colored the static features, which would correspond to things like height and wingspan. I've colored those in orange. The things that correspond to actual motion are blue, and then green are those 22 things that describe the events. And you can see here that the static features are still pretty important. They're accounting for about 23% of the overall entropy gained by this model. And if you look on the left of this, you can see that they're still the most important features. And this makes sense, right? Because things like height are going to be very consistent from one replay to another. So your height doesn't really change over time. And so, of course, the model is going to try to grab onto the very consistent values first if it can use those, right? But looking at height and so on are the most important individual features doesn't tell the whole story because, and also I should mention, this is where the 4,000 users metric that I mentioned earlier comes from. So if you look at the number of bits of entropy that are derived from all these orange features here, it's enough information on its own to uniquely identify about 4,000 users in theory. This is why I mentioned that those studies earlier with up to 500 users don't necessarily prove that motion is being used to identify users. But if you look at the blue features, the motion-based features together, those account for about 74% of the information. So the vast majority of the information that is actually being used to identify users in this case are the actual motion-based features, right? And so this indicates that, essentially the results of 94% accurate identification wouldn't have been possible anywhere near that without actually taking advantage of the motion data. And then lastly, the remaining 3% or so are those context features about what the events are in the game that users are reacting to. So not insignificant, but by far the least important type of data. So I'm going to conclude here by trying to put this result in context, right? What does it mean that we were able to uniquely identify 55,000 users based on their motion alone, right? How does it compare to biometrics that we might be more familiar with, like fingerprints and iris scans? Well, it turns out NIST has done a lot of really good studies on the accuracy of conventional biometrics. In particular, there's this 2006 study from NIST that looked at a lot of commercially available fingerprint reading solutions. And at the time, they put fingerprint readers at about here on the graph, so able to uniquely identify 20,000 to 30,000 users before you get a high degree of false positives. And it turns out iris scanning is even worse. So iris scanning is only really able to uniquely characterize about 10,000 users before you see the error rate increase dramatically. On the other hand, there are some biometrics like facial recognition that happen to be off the charts here. So facial recognition, you can tell apart 100,000 users or more based on their faces. And I should point out, right, of course, fingerprints and iris scanners and all that has improved since 2006 and 2012 when these studies were conducted. But this is also the very first study on motion data identification at this scale in VR. And so the techniques for motion data are also likely to improve over time, right? So overall, we can conclude it's fairly comparable, the degree to which you can identify users from motion compared to a lot of the commercial solutions for fingerprinting and iris. And what this means is that just by using a VR application, this data of movement of these three tracked objects is fundamental to the way the metaverse works, right? In order for someone else to see your avatar on their screen, they have to get some amount of data about your motion just to render that. So it would be like if by browsing the web, we had to upload a picture of our fingerprints to every website we visited. That was just how the web works, right? Of course, on the web, you don't have to do this. You can clearly separate the data that an application needs and an application doesn't need. But here in VR, it's the very same data that makes the whole experience possible, this motion of these tracked objects. That is the exact same data that can identify you out of tens of thousands of individuals. And this presents a really important opportunity for privacy researchers to look at how these applications can still function without revealing quite so much information about the users. And with that, I'm happy to take any questions. Thank you.
All right, thank you very much. I want to see, are there any questions from the internet over the phone line?
Oh, hey, Benny. Okay, Benny, you have a question?
Hey, what's up, Vivek? Can you hear me well?
Yeah, I can hear you.
I had a question about the headsets as a feature for identification. You mentioned that the Windows mixed reality lowered your the rate at which it could be identified, and that could be because of the tracking. But I see some other headsets listed there that seem to kind of be counter evidence for that explanation, like the Pico 4 and Vive Pro, which have the same kind of tracking as the Index, but negatively affect your identification accuracy.
So I think part of this, right? So Vive Pro and Pico 4 are still on the V1 base stations, right? Index is the first to have these V2 base stations for Steam VR. So I wonder if that accounts for part of it. There could also be a skew in terms of the user base, right? So it could be that Index users is a $1,000 headset. You've got to be pretty serious about virtual reality to buy a $1,000 headset. And those users might be more likely to be experienced at developing this muscle memory and so on. So I think there's probably a mix of technological explanation as well as maybe just in terms of the target users for those devices.
Yeah, thank you.
Thanks, Benny.
Do we have another question?
Hi, this is Sachin Deshpande from Qualcomm Ventures. Hey, Alan, thanks for inviting me. And Vivek, great presentation. I mean, I really, really enjoyed it. You know, I just had one question kind of relating to the background you set, you know, with the original study in 1977 and now. Based on the data and the motion that you're seeing and you're tracking everything, are you able to see just even before the uniquely identification of individual people, are you also able to do just clusters? And the reason I ask this, there's a business background. I'm just curious, in case there's a privacy nightmare of some sort, you know, even if it's a false privacy, narrative, sometimes you can get away by just clustering people, like gender, or you know, different types of groups, or that sort of thing. So I'm just curious, were there high-level segmentation stuff that you could get even easier from way back when, and or even now that you found before you got really, really deep with the model here?
Yeah, that's a great question. So one year after the original Cutting et al. Study, they tried to answer this question. So they did a study in 1978 where they looked at these same recordings and they asked random strangers, can you guess the gender of the person who was in your observed? And that also, they were able to do that with a high degree of statistical significance. And then more recently, 2007, there was a study that did basically the same thing for age. By that time, we were already using machine learning for problems like this, but looking at children versus adults in a lab. And then most recently, here at RDI, we've had studies, small scale with 50 people, sort of escape room style study, where we were basically told people to just play a game in VR, and in the background identifying these 30+ attributes about them, just based on the way they play the game. So there's a lot of evidence that you can extract a lot of demographic information from users, in addition to just identifying them. And again, the problem here is not only is the demographic information embedded in the data that you're sharing with the application, right? In a metaverse environment, that same motion data is visible to all the other users in the room with you, right? It's being streamed to them to make the application work. And so it's not just the application, it's everyone else, potentially strangers, that are learning a lot of demographics, a lot of information about you, whether you really realize it or not. And so we've looked at, I think clustering is quite hard because you're looking at really composite metrics across a lot of axes that are being used to identify people. But we have looked at things like differential privacy. There was a study called MetaGuard that we did, try to use differential privacy to obscure some of these attributes. And this is an active area, so we're hoping to do more rigorous defense techniques in the future as well.
Thank you.
Great stuff. Thank you very much.
Thanks.
There's a question from the chat box from Daniel asking whether the decision tree features that you constructed implicitly actually estimated the room size or the orientation of the player.
I don't think so. Room size is pretty hard to look at from 1 second or 2 second motion segments. So in the metadata study, which is what we call the escape room study, we were able to discern room size. And the way you do that is you watch users for minutes at a time exploring the entire boundaries of their room, and then you can take the limits and kind of get the dimensions of the space they're working with. When you look at the featureization here, you look at the 1 to 2 seconds of data, that's not enough time within a feature for users to explore the boundaries of the room. And that's why I doubt that the features are including room size. In terms of orientation, that could potentially be encoded in the data if people stand in a certain way, if they look a certain way. But again, because we're looking at cross-session identification, it's only going to be able to identify users based on that if it's consistent from one day to the next to the next. They always stand the same way. They always look the same direction. And in that case, we do want to use that data because that is unique to the user. That is fair game in terms of classifying them based on that if it's a consistent behavior.
Thank you. I want to ask a question that one of the challenges that you show is recognizing 55,000 people, right? But when you think about user identification on the smartphone, it's actually one versus the rest. So in the sense that you could have a 0-1 classifier for each one of the users.
Yeah.
And then, so that solves two problems. Number one is that you can always train yet another classifier, no matter how many users you add, right? So, you know, for the smartphone, really you can switch as many users as possible. You always can get a classification. And the second one is that you can also use one versus the rest to reject outliers, because one classifier, you know, whether it's a weak or strong, only responds for saying yes or no for one person. And whether the rest of the person is within the rest of the 55,000 or even someone unknown, I just say no, one versus the rest. Do you think that if you apply the same feature set in a one versus the rest fashion, do you think that the classification result may be similar or may be different?
Yeah, so actually internally, like LightGBM is using a multi-class OVA one versus all classification model. So internally, right, what this is doing is training for every user 200 trees that are looking at that user versus all the other users' data. And then, but even that has a performance bottleneck, because if you're looking at all here, you're trying to train, you know, 55,000 users worth of negative samples every single time. So you're doing 55,000 squared. Yeah. You know, and so when we look at one versus all here, in the hierarchical approach, the all is subsampled. So it's not actually all, but it's enough to look at what stands apart about this user. But it is essentially internally, it's a multi-class OVA one versus all approach that's being used here.
Okay, thank you.
Yeah, I have a question. First of all, it's very brilliant presentation, and I really love the impressive illustration. You compare this with a fingerprint data set. The question I want to ask is do you know why the sequential model fell short in your experiment? I hear you that you're talking about LSTM that doesn't work well, but as far as I see from your feature set, it's for every feature point it's made of 1 second of motion features, then some context features, and another 1 second motion features. It's the first, my math interpreted wrong. First 1 second, it's one pose, and the second. The motion feature at the last second pose. It's like you were trying to distinguish person by looking at discrete poses. But I just feel like it's kind of counterintuitive for humans who usually look at a sequence of poses to recognize the patterns. Yeah, I see the model is really doing well, even just looking at discrete poses. So why it cannot digest a sequential data?
Yeah, so we can kind of speculate as to why the sequential model failed. I just want to point out, right, in this prior work, so this one at the bottom, this Plouffer et al. Is using a LSTM model, right, 40% accuracy, and then the rest of them are using some kind of tree-based model. So just to say that prior work kind of supports, we're not the only ones who have found empirically that sequential models happen to be performing worse. So why is this the case, right? So if you think about it, I think it comes down to the amount of data that you have per user, right? Sequential models like to have, on a per class basis, a relatively large training size. Now, if we look at this data set here, just jump forward. So if we look at the Beat Saber data, right? So we have, you know, on a per user basis, we have on average something like 5 to 10 replays per user. If you split that up into samples, into 1 second samples, you have hundreds of samples per user. But if you just want to look at sequences, right, on average, after doing train, test, split, and all that, you might have 5 or less sequences to train for each user. And so 5 or less inputs ends up being a little bit too small for sequential model to understand the user just from 5 sequences. Whereas we split it up into 1 second, then we have, right, hundreds of inputs to train on per user. So I think that's part of the picture. Part of the picture is you need this huge sequence of input, right? And so there's just computational constraints of building a big enough model. We found when we tried an LSTM model that it actually got confused when the user is moving around. So the best performance in the LSTM model came from like the first 1 second of the song where the user is just standing stationary and it can measure the height nicely. And you put a longer sequence into the model where the user is actually cutting blocks and the performance goes down. It doesn't have enough context to really understand that. So that's kind of our empirical observation.
Thank you. I guess this is going to be the last question for today. There is a question from Natalie, and then she asked that will your conclusion apply to uniquely identified participants in social VR based only on how they move?
So will it apply to identifying
other than playing games?
Yeah, it's a good question. So we don't have a large data set to validate this, right? So there's two kind of sub questions here. One is if you train on users in VR chat, for example, and then test on users in VR chat, can you identify users, the same users within VR chat? I think the answer there is almost certainly true. Again, we would need to have an equally large data set to validate this for sure. And this mechanism of uploading the recordings, that's pretty unique to Beat Saber. That doesn't really exist in other applications. So it's hard to answer for sure, but I think almost certainly in other applications, you'll be able to identify users to some extent, because all of the prior studies with 500 users or 30 users, those are all from different kinds of applications, watching videos, bowling, archery, right? There's a wide variety of applications. They've all shown some promising results. Another, I think, even more interesting question is, can you do it across applications? So can you look at training your model based on Beat Saber users, and then using only the Beat Saber data, could you identify one of those Beat Saber players if they're just using VR chat or something, right? And that's a little bit harder. I think that's also probably possible. But that would be a pretty interesting use case is, can you identify people in a completely different application from where your training data originated? If you could, then you would have a really powerful ability to track an individual across all of the different applications that they use and correlate correlate the same identity in one benign application like a meeting versus some application they might not want to be identified in, but you could do the cross application identification as well. So that's an interesting area of future work. But as to whether this just directly applies to other applications, I would imagine that you could do similar things in other contexts.
Thank you. In the interest of time, lastly, since we are going to make this recording available online, if any viewers want to get in touch with you after the talk, how can they contact you? Is there a contact information?
Yeah, so you can, you're welcome to look at the RDI Metaverse Research website, rdi.berkeley.edu/metaverse. And the paper is linked here, the archive link. And the contact details for the authors are in the paper. So you can contact any of the authors from the emails in the paper.
Thank you so much. Thank you, Vivek, and thank you everyone making your time available online to join our discussion today.
Thanks, everyone.